I didn't give you any homework, did I? I think I forgot to. Oh, did I? Oh, okay. Okay. Oh, good. Uh,
The second problem in your vibrations is
uh-huh.
like the second proof you did. So
Yeah.
the first time you did the first proof, and then the problem you assigned was basically the same thing.
Right. Yeah.
So I thought you were going to do kind of the same thing.
Oh, yeah.
One problem, just the proof that you
Uh-huh. It's a good idea, though. I know, exactly. Right. All homework from now on is suggested. But yeah, exactly. I strongly suggest that you don't stop doing homework. That's my strong recommendation. Okay, no homework questions. So we're going back to vibrations. So I have a reverse pendulum. Sure. With a spring? Or what? What makes it not fall down? No, that's here. But how would it? Doesn't it just go like this?
Well, like if you know the doors that have springs.
Yeah.
So that they
yeah.
bounce back and forth, just having that vertical.
Oh yeah.
What is the force that's required in vertical after applying a force? So the reactionary force.
Like if you flip the spring thing?
Yeah.
And it just vibrates? But now I'm. Yeah, I don't know. Now I'm. I think that would be like a combined deform dynamics question. It's a good idea. Yeah, because it would have to do with it would have to do with bending deflections, But yeah, just well, we're not going to do that right now. I need to think about it before I could do it, for one thing. But let's do this question. I'd like you to try to work through this together. If you get stuck, talk to each other about it. Ask me about it. But what? Oh yeah, come get it. Come get it. And imagine this isn't going to start going crooked, like it has something to hold it in line. I guess we're always assuming that on these vertical ones, like they would get sort of. Oh no, you can skip that. But that's a good question. They would be there. So derive the. Let's say, well, okay. So first I have to give boundary conditions. So let's say that it's pulled down 1 centimeter from its hanging equilibrium position. What's the position is a function of time. where that's x. And what's the frequency? Okay, so I'm going to start with the free body diagram.
Wrong.
And I'm going to treat it as two separate springs. The one at the top, 1 over k is equal to 1 over 100 plus 1 over 500. So that is 6 over 500. So k is 500 over 6. What's that? 83.3 repeating. And then the force that the top spring applies is has a magnitude of 83.3 repeating times x. And now let's think about the direction. So if you have a positive, if you move that thing in a positive x direction, the force is going to be downward. So this has to be negative. What? Yeah, but I'm just trying to figure out the relationship between, so I just always draw my arrow in a tension direction and then put the, so we're a long way from the boundary conditions. And then this one, well, I guess, and I always do it like this. I'll do it like this again. Okay. So if you, and the magnitude here is going to be 400x. If you move that in a positive x direction, this is positive, so that's right. And you could put in the reaction forces on the wheels there, the horizontal forces. You know that the x component of acceleration is going to be 0, so you just get that those are equal to 0. So the weight, yeah, there is weight. And that's 9.81. Oh, so, okay, you know what? That's a good question. Yeah, that's right. So I'm choosing my x equals 0 to be at the hanging equilibrium position. And I did that. So we did the one derivation that showed that if you choose your x to be at the equilibrium position, you can do this problem kind of as if there's no weight, And so, yeah, calling this a free body diagram is it's not really accurate because I'm not including the weight. But these spring constants are, like the way I have these spring forces set up is designed to eliminate the weight from the problem. Do you remember doing that? So if these were really true spring forces, our x equals 0 would have to be at the spring's resting length. And then you'd have the weight going down, and then the weight would cancel with the spring forces that are applied when the thing is down in its equilibrium position. And so, I hadn't really thought of it this way, but I would say, let's think of this as the free body diagram, because what? It is a free body diagram. Well, let's think of it as a correct free body diagram, because the fact that we're using our x equals 0 to be at the hanging equilibrium means that we're canceling out the weight force. You know what I mean?
Weight is included in the spring.
Yes, exactly. Weight is included in the way we've defined it. Okay, so let's do it like this. That's a super important question. I hadn't really thought of it like that. Otherwise, we'd have to go through all the thing with the cancellations. That seems like you've already done that in the derivations. Seems like sort of unnecessary extra work. Who's with me on that?
Isn't it true that it's going to apply, it's going to take less force
To less force to what?
to move the mass downward?
Yeah, you would think so. I mean, but we found like that was sort of a surprising thing. If you look back at the notes from the day that we did that hanging mass derivation, it's actually not true. It's like this behaves exactly like a horizontal spring mass system with just a slightly different resting length. That's still sort of counterintuitive to me, but that's how it is. Right. Yeah. Uh-huh. Yeah. Right. Yeah. So now in the positive x direction, we could also think of this as in the positive x direction, negative 400. So we have negative 483.3 repeating times x is equal to the mass times the x acceleration. And so x double prime plus 483.3 repeating x is equal to 0. And so if you think of this as the natural frequency squared, then our solution, our general solution, is A times the sine of the quantity square root of 483.3 repeating times t plus phi. What's square root of 483.3? 21.98 t plus phi. Now we're going to use our boundary conditions. And we know that at time equal to 0, x is equal to 0. And at time equals 0, x dot is equal to 0. Yes, negative, thank you. Yeah. If those are your boundary conditions, it's a very boring system. Okay, so at time equals 0, well, let's do the derivative one first. So x dot as a function of time is equal to 21.98 a sine, a cosine of the quantity 21.98 t plus phi. And so at t equals 0, we have 21.98 a cosine of phi is equal to 0. And so phi is equal to pi over 2 or negative pi over 2. I'll choose pi over 2. And then update the x function. So this is equal to a sine of the quantity 21.98 t plus pi over 2. And so at t equals 0, we have that a times the sine of pi over 2 is equal to negative 0.01. So a is equal to negative 0.01. And so our final answer for the function, x as a function of time, is negative 0.01 times the sine of the quantity 21.98 t plus pi over 2. Yeah. And then for part B, we want the frequency. Well, we know that the natural frequency is 21.98. The actual frequency is 1 over 2 pi times 21.98. So what do you get for that? 3.50 hertz. Any questions about that? Okay, let's do one now where, yes. Mm-hmm. Oh, yeah, well, I put it in the free body diagram as two separate forces, and then when you, they had opposite signs, but the arrows were in opposite directions, so then when I made the arrows in the same directions, they were just, it was just like, it was a negative 83.3 times x and a negative 400 times x, and so you can just add them, they both had an x. Yeah. Well, the way that I always do this is I don't know. I bet 5 people in the class have better ways to think of this than the way I think of it. So I'm not sure I totally recommend this, but I always just think, okay, a spring applies a tension under certain conditions. So the first thing I do is draw an arrow as if that spring's applying a tension. And I know the magnitude is the k times x, so I write k times x next to that arrow. And then I think, then, sometimes it'll be positive and sometimes negative. So then I think in our specific case, with the way the spring is set up and the way the coordinate system is oriented, I think of moving the body in the positive x direction. And I think, does that apply a force in the direction of my arrow or a force opposite the direction of my arrow? You know what I mean?
That's why it's negative.
Yeah, so in this case, if you move this in the positive x direction, this spring would be pushing on it, and so I needed the negative there. It would be in the opposite direction of that arrow. In this one, if I moved it in the positive direction, I'd be lengthening that spring, so the spring would be in tension, and so I didn't need the negative here.
You're calling it negative.
I'm just thinking of it as force directions. If you make a spring longer, it's going to be pulling on the thing. If you make it shorter, it's going to be pushing on it. So for this spring, if I move the body in the positive x direction, I move it up. That puts this spring into compression, so the force would be opposite my arrow. So I put the negative. In this case, if I move it in the positive x direction, I'm lengthening the bottom spring, and so it would be in this direction, so I kept it positive. That's how I think about it. It has the sort of the annoying quality of like you have to do actual thinking each time you know what I mean. That's sort of a nuisance. I'm sure there are ways that there are plenty of ways to do it where you just always have that same magnitude of force, but
Now we're
yeah.
Yeah, he keeps a little clicker back there. He watches all of us while we take the test.
Typically just go straight to free body diagram that just has the spring forces. I was doing one with like mg and force applied, and then I was gonna add another free body diagram with like the equilibrium.
Yeah, so
Do all the substitutes.
I had not thought about it. Yes, I had not thought about it this way before, but you know, this is not. If the weight was on here, this would not be an accurate free body diagram because I have my x equals 0 at the hanging equilibrium position. You know what I mean? It would only be, if I had the weight on here, this free body diagram would only be accurate if my x equals 0 was the spring's resting length. Okay? But since I have my x equals 0 at the equilibrium position, this is accurate because that little bit of extra stretch or whatever that put it in the hanging equilibrium accounted for the weight. And so I think this is the way, and I hadn't thought of it this way until this class. So, but so I hadn't talked about it this way before, but I would do it like this. This is an accurate free body diagram because since that x isn't a distance from the resting length, it's a distance from the hanging equilibrium, the weight is accounted for.
The force, that's in the boundary conditions, force applied. That's where that, because we have to pull it down, right? So
The force to pull it down is a boundary condition, yeah. That's right. So this free body diagram always represents during the oscillation. It doesn't represent putting it into the boundary condition, into the initial condition. Any other questions about that? So let's do one now where the motion of the system. So we're going to use a linear spring, but it's going to be the oscillation is going to be a rotation. So, let's start. All right. So let's say that we have a disk that rotates around its center. The radius of the disk is 0.1 meters. The mass is 0.5 kilograms. And at this point at the bottom, there's a linear spring connected to the wall. Okay, so this is a pin that it rotates around. And let's say that the spring constant here is 500 newtons per meter. What's the frequency of this system? So the way to do problems like this, so we're only dealing with 1 degree of freedom systems. So identify what you're going to call your 1 degree of freedom. In this case, we're talking about the angular motion of that disk. Okay, so we're gonna do this all based on an angle theta of that disk from its equilibrium position. Okay. Yeah, but then the only difference is now, yeah, right. We're going to set it up just like a torsion spring problem, but now we have to represent represent torsion spring was given in terms of that angle. This isn't automatically given in terms of that angle theta, but we can represent it in terms of that angle theta. So we're going to choose our variable that's going to represent the motion, and that's going to be theta. And then whatever forces we have, we need to express in terms of that variable we've chosen. So let's draw a free body diagram. There's an unknown reaction force at the middle that isn't going to come into this. And then there's a force applied by that spring that for now it has a magnitude of 500x. And then that would be negative because if this point moved in the positive x direction, that spring would shorten and push back this way. So there's the free body diagram. But now we have two variables. So now we want to express x in terms of our chosen dependent variable theta. What makes it a dependent variable? Why do I call that a dependent variable? My taxes? What about my taxes? Oh yeah. That's a pretty good one. I gotta admit, Fred, that's you've now said one funny thing this semester. No, it's because it's a function of time, and we're always heading towards that ordinary differential equation where we're solving for a position dependent variable of the independent variable time. Okay. Okay, so what's the relationship between, so if you move this some angle theta, how much does that change? Well, theta is equal to the radius, x is equal to the radius times theta. That is equal to that is arc length, which actually, yeah, that sort of brings up the fact, doesn't it, that we really want arc length. We want this to be r sine theta. But we really want a true x here, I guess. I mean, we don't want a rounded distance. You know, we don't want the arc length around that circle. We just want the x position. So here. So if this is theta, this is what we want. This is r sine theta. And so that was a
Okay there, one time I finished it.
Okay, so let's try this free body diagram again. You probably just got that dependence joke. Okay, so we have our reaction force R, and now this we can write as negative 500 times the radius 0.1 times the sine of theta. So negative 50 theta. I keep wanting to get rid of that. We will eventually. I think I said 0.1, didn't I? All right, so now we'll use the moment equation about the pin, which in this case is the center of mass of the disk. There's no moment produced by that reaction force R. What's the moment produced by that spring force? So it's going to be, it's going to be negative moment arm of 0.1 times this force of negative 50 sine theta is equal to the mass moment of inertia about the hinge, which is the center of mass of that disk, times alpha. The moment of inertia of the disk about the center of mass is 1/2 times the mass, what was that, 5? Times the radius squared. So that's 0.0025. Yes. I put one extra negative in there. Right. If we assume it's going this way, that would be a positive moment, but then our magnitude is negative. So there's only one of those negatives. And so we get negative 5 sine theta is equal to 0.0025 alpha. And so what's 5 divided by 0.0025? Okay, so 2,000 theta is equal to 0. I took it away. We still have that sine is equal to 0. And so now this is for all oscillations. Yeah, so we can come up with an explicit closed form solution if so we can find a closed form solution if theta is always small, because then sine of theta is always about equal to theta, if we're talking about radians. And so we get theta double dot plus 2,000 theta is equal to 0. And so the natural frequency is equal to square root of 2,000. What's that? $44? 44.72. That's 1 over seconds. And so the frequency is 1 over 2 pi times 44.72. And what do you get for that? So 1, 2 hertz. Okay, so we're going to do more problems where what you choose as your sort of general variable, what you choose as your 1 degree of freedom variable, is different than what you would naturally choose for those loads. And you just have to go through the process of representing those loads in terms of what you've chosen as your generalized variable, and then go through the calculations. Yep. Oh, no, that's a good point. I just left it off, but I should have put it in there. But it just doesn't produce a moment, so it doesn't come into it. Okay, that's all.